Good evening, everyone. From today onwards, I will be giving a series of lessons on A-level chemistry, starting with this topic called atomic structure. This is one of the first few topics covered in most of the JCs in Singapore. So I'm covering the A-level chemistry syllabus with this topic, atomic structure. So this is the content and the learning outcomes for today's lesson. Okay, I shall not go into the details because I will be sharing each objective as we carry on with this lesson. So the lesson outcome include atomic structure, nucleus of atom, electronic structure, electronic configurations, electrostatic effects, atomic radius, ionic radius, IE, which is known as ionization energy, and lastly, electronegativity. Here are the references for the A-level chemistry syllabus. Now, atomic structure. So starting with what is an atom? An atom is the smallest particle found in an element that can take place in a chemical reaction. So atom consists of a small dense nucleus surrounded by electrons. And in the nucleus, there are protons and neutrons, collectively known as nucleons, and they contain the bulk of the mass of an atom. Nucleus consists of protons, which is positively charged, and neutrons uncharged. Electrons are found outside the nucleus, called the extranuclear space. They are negatively charged and concentrated in certain regions of space around the nucleus that we call them orbitals. Atoms are very small. They only have a diameter of around 10 to power of negative 10 meter. The nucleus of the atom is even smaller, with a diameter of only 10 to negative 15 to 10 to power negative 14 meter. And the region around the nucleus where electrons move is mostly empty space. Now, these are the important properties of the subatomic particles, protons, neutrons, and electrons, discovered by the various scientists and the experiment associated with the discovery. Where are they located? Their actual mass in kilograms. You can see that electrons is much smaller compared to protons and neutrons. Therefore, electron is considered of negligible mass compared to protons and neutrons. Therefore, we convert this mass into relative mass by taking the actual mass divided by the mass of the proton or neutron. Therefore, protons and neutrons have relative mass of 1 each, and electron have a mass of 1/1840 when you take this 9.11 divided by 1.67. This is the charge of each subatomic particle, plus 1.6 times 10 to the power negative 19 from proton, and electron is the same magnitude but negative. The number seems to be very small, so we convert it to relative charge, where protons has a relative charge of +1 and electron -1. And these are the symbols of protons, neutrons, and electrons. Now, looking at the behavior of subatomic particles in an electric field, consider the following beams of subatomic particles traveling at the same speed. All right. So when each of these beams is passed through an electric field, each beam is found to behave differently in these aspects: the direction of deflection and the angle of deflection. Now, for proton, because it is positively charged, it will be deflected towards the negatively charged plate. As for electrons, which is negatively charged, it will be deflected towards the positively charged plate with an angle larger than x because it has a much smaller mass. Having a much smaller mass will means that it deflects to a greater extent. As for neutron, it was not deflected because it is uncharged. So the angle of deflection is 0 degrees. So the direction of deflection is dependent on the charge of the subatomic particle. The angle of deflection is proportional to the magnitude of the charge over mass ratio of the particle. The larger the charge of the particle, the stronger is the attraction towards the oppositely charged plate, and therefore the greater the angle of deflection. However, if the mass of the particle is larger, it will be more difficult for it to deviate towards the oppositely charged plate. Therefore, the angle of deflection will be smaller. Now, this is a simple word example. You can pause this video before you attempt the question. Ignore the answer. Try to do yourself before checking the answer. So, beams of charged particles are deflected by electric field. In a particular experimental setup, protons are deflected through an angle of 10 degrees. Assuming an identical set of experimental conditions, by what angles would the beam of each of the following particles, all traveling at the same speed, be deflected? So for hydrogen ion, the charge and the mass ratio is 1. Okay? The charge of this particular particle is +1. The mass is 1. So 1 divided by 1, 1. And the angle of deflection is 10 degrees. Now, if you have a particle with 2 times the mass, the ratio becomes half. And because it is of a larger mass, so the angle of deflection will be half of 10 degrees. For the next one, the oxide ion with a mass of 18 and a charge of -2, it will be 2 divided by 18, which gives you 1/9. The angle of deflection will be 1/9 times 10, which gives you 1.11 degrees. As for the next particle, it has a mass of 9 and a charge of +2. So 2 divided by 9. And you take this, multiply by 10, will give you 2.22 degrees. Now, the nucleus of the atom. A nuclide of any species of a given mass number and atomic number can be represented using this, with the nucleon number at the top left-hand corner of the symbol, and the bottom left will be the proton number. A is the nucleon number, where number of protons and electrons added together. Number of protons is Z, and number of neutrons is A minus Z. So this is an example. Uranium, you have 238 for nucleon number, proton number 92, number of neutrons is 146. Where you take the nucleon number minus the proton number to obtain the number of neutrons. And the number of electrons will be 92. The atomic number or the proton number determines the identity of the atom. For example, every atom with atomic number 6 is a carbon atom. It contains 6 protons in its nucleus. The nuclide of an element is named by its elemental name followed by its mass number. So we name hydrogen followed by the mass number. So these are the isotopes of hydrogen: hydrogen-1, hydrogen-2, hydrogen-3. And we have the isotopes of carbon, carbon-12. 12 represents the mass number of this particular isotope. So it brings us to this concept of isotopes. Isotopes of an element are atoms that contain the same number of protons but different number of neutrons in the nucleus. So chlorine is a classic example. They have the same number of protons because it is of the same element, but the number of neutrons will be different. So because isotopes still have the same number of electrons, the chemical properties are the same. Chemical properties are determined by the electron. So if these two particles have same number of electrons, the chemical properties will be the same, meaning the type of chemical reaction it undergoes and the formulae of the compound form will be the same. Now, isotopes have different number of neutrons, so they have different masses and hence different physical properties like density and melting point, etc. Now, I shall not go through the word example 2 here. Okay, it is very straightforward. But let's look at this example. Maybe you can pause the video, attempt the question first before checking the answer to verify whether you have understood the concept. Word example 3, with the aid of the periodic table, identify X and Y below. A. Some isotopes are unstable and decompose naturally. An example is potassium-40, which undergoes decay by beta particle emission, as represented by the equation. B. Each uranium-235 atom split into 2 smaller atoms and 2 neutrons, with the release of energy as represented by the equation. So, what is X and Y? So, to solve for A first, okay, write down the equation. Determine the nucleon number of X first. So, based on the equation, the particle only emit beta, so there's no change in the nucleon number, which means X has a nucleon number of 40. Now, however, the number of proton is 1 less in the original potassium because there is a gain of electron by the beta emission. So the number of proton will be higher than K because it's -1 here. So it is 19 minus -1 to give you 19 plus 1, 20. So the element is calcium. For part B, given the equation, the nucleon number of Y will be 235 plus 1 minus 90 minus 2. 2 because there are 2 neutrons emitted. So the nucleon number will be 144. Then the number of protons in Y will be 92 minus 36, which gives 56. So the calculation is based on the law of conservation of mass and charge. This shows the historical development of the atomic model, which I will not elaborate in this lesson. Okay, it shows how the model evolved over time. And for our lesson, we will focus on the last one here, the quantum mechanical model. Now, so in this model, what do we know about the electrons? Electrons in the atom do not occupy fixed positions around the nucleus. They do not actually move in orbits or fixed circular path around nucleus where you learn in O-level. That is not what the model says under quantum mechanical model. In fact, in the theory, electrons in the atom move in certain regions of space known as atomic orbitals, where each electron has energy that's quantized, where each electron has energy restricted to certain values. Each electron occupies a discrete energy level. So electrons are not moving in orbits. They are actually moving in spaces known as orbitals. So they are not moving like the planets around the sun. That is not correct, or that is not the updated model. They are actually moving randomly. So the arrangement of electrons of atom or ion is referred as electronic structure. The electronic structure provides us with this information. Number one, the number of electrons in the atom or ion. Number two, the distribution of electrons in the atom or ion. Number three, the energies of the electrons. It is important because it determines how the atoms will react with other atoms to form ions or molecules. So, around the nucleus, we have the principal quadrant shells. First shell, second shell, third shell, etc. And each shell contains subshells, and subshells contain orbitals, and orbitals contain the electrons. So this diagram shows the relationship between shells, subshells, and orbitals. So the entire diagram here shows the shell. We call it principal quadrant shell. And within the shell, we have subshell. This is called the 2s subshell. And this is called the 2p subshell. Okay? And within the subshell, there are different orbitals. For the 2s subshell, there's only one type of orbitals. But for the 2p subshell, we expect to see 3 different orbitals in the x, y, z orientation. Now, electrons in atoms are arranged in a series of shells of energy levels surrounding the nucleus. Each shell is described by a number known as the principal quadrant number. The principal quadrant number n is a positive integer n equals to 1, 2, 3 number outward from the nucleus. The greater the value of n, the further the shell is from the nucleus, and the higher the energy level of the shell. And the weaker the electrostatic attraction between the nucleus and the electron, and the larger the size of the orbital. All the orbital become more diffuse, meaning the electrons are more randomly distributed. All right. Now, this diagram shows the shells of energy level corresponding to the different principal quadrant number. N equals to 1, N equals to 2, N equals to 3, 4, 5, 6, 7. And the subshells, sublevels, or the orbitals. Each shell comprises of one or more subshells. Each subshell in turn comprises of one or more orbitals. An orbital represents a region of space in which there is a high probability of more than 95% of finding an electron. And each orbital can accommodate 2 electrons. And each orbital has a distinctive geometrical shape. The energy of an orbital is the energy of the electron occupying the orbital. So this shows the relationship between principal quadrant number and the type of subshell. 1, you have the 1s subshell. 2, you have the 2s and the 2p. 3, 3s, 3p, 3d. 4, you have the 4s, 4p, 4d, and 4f. And this shows the relationship between the subshells and orbitals. S subshell contain 1 orbital. The types of orbitals is S. P subshell, you have 3 orbitals. You have X, Y, Z orbitals. And D, you have 5 orbitals. You have 5 different types of orbitals here. As for F, we shall not go to it. It will not be covered in the A-level syllabus. All right. So you can see if the number of shells is n, the number of subshell will be n. 1, 1, 2, 2, 3, 3, 4, 4. All right. All right. Shapes of the orbitals. We have the S orbital, which is spherical in shape. We have the p orbital, which is described as dumbbell. D orbital in various shape, not fixed. There's no specific name for it. All right. So let's start with the S orbital. The S orbital starts with the letter S, spherical. Now, they are non-directional, meaning the electron density is not concentrated in any particular direction. All right. So they are found within the region that was displayed. The s orbital of different shell have the same spherical shape but different sizes. As n increases, the s orbital will increase in size. 1s is smaller than 2s, 2s is smaller than 3s, 3s is smaller than 4s, and the orbitals become more diffuse. For the p orbitals, the shape of the p orbital is dumbbell shape. There are 3 orbitals, x, y, z in the p subshell. The p orbitals are directional as the electron density is concentrated in certain directions along the x, y, z axis. The 3 orbitals have the same principal quadrant number and are degenerate. Degenerate means they have the same energy. So x, y, z are of the same energy level. And p orbitals of different shells have the same dumbbell shape, but different sizes. All right. So you expect a principal quadrant number 3 to have a larger size of p orbitals than the one from 2. So as n increases, the p orbital will increase in size, with 5p having the largest size and 2p the smallest. And the p orbital is known to be more diffuse because there is a greater unevenness in distribution of the electrons as the orbitals grow in size. As for the d orbitals, we have 5 there. They are in the d subshell. All right, dxz, dxy, dyz, dx squared minus y squared, dz squared. They're referring to different dimensions. So these 3 orbitals here, xz, xy, and yz, they have similar 4-loop shape. Okay, so this is the region where the electrons are moving. All right. 95% of the chance you will find the electron there. And these orbitals have their loops pointing between the axes. Whereas this orbital, x squared minus y squared, also has a 4-loop shape, but its loops was aligned along the x and y axis. So it's quite different from the alignment for the first 3 orbitals. As for the 5th one, it looks like a dumbbell surrounded by a small donut-shaped ring at its base. This orbital is aligned along the z-axis. Okay, so they are quite similar in shapes, but their alignment along the axis will be different. Let's look at the relative energies of the orbitals. So this is a diagram showing the relative energy level of the orbitals, not to scale up, in a multi-electron atom, meaning this atom got more than 1 electrons. So we have the 1s at the lowest level is in the n equals to 1 shell. N equals to 2 at the 2s and the 2p. Okay, so each line represents an orbital here. And 2p is 1 subshell, 2s is another subshell. And we move on to n equals to 3. We have the 3s, 3p. And take a look at this. Instead of 3D, we have 4s of a lower energy level than 3D. So 3D is higher than 4s. So electrons are filled in the 4s orbital before the 3D. Okay, and then we have the 4p. All right, and then the 4D, and then the 4f. Now, so for orbitals within the same shell, the relative energy increases in this order, SPDF, with F of the highest energy level and S the lowest. Now, the diagram shows how orbital energy decreases with increasing atomic number of the element. So as the nuclear charge increases, the energy of all the orbitals will decrease based on the information here. The energy of the electrons occupying these orbitals will also decrease. Why? Due to the proximity of the nucleus, the spherically symmetrical s orbitals are actually affected to a greater degree than the more angular p and d orbitals. So we will expect to have the energy of the s orbitals to decrease more rapidly than all other types of orbitals. So if you look at the diagram, there is a drop for every orbital energy level, but it is more significant with S because of its proximity to the nucleus and the spherically symmetrical shape it has. So it is affected to a greater extent compared to the other orbitals. By n equals to 4, there is, in fact, an overlap between the third and the fourth shell. As seen from the graph above, the energy of the 4s orbital has already become less than that of 3d. For example, we look at atomic number 18. Okay, we can see that the 4s has become lower than the 3d. 4s is here, so 3d is here. Can you see that? So 3d, okay, in fact, some of the energy of the 4s is even lower than 3d. There's some overlapping over here. Okay. So this is a summary of what I have gone through for the first 20 minutes. I shall not go through now. Now, let's move on to writing electronic configuration in SPDF format. Now, the electronic configuration shows how electrons are arranged in the shells, subshells, and orbitals. So the first method is the O-level format, the earlier model. But what we are going to be learning today will be part 2 and part 3, the SPDF notation and the electron in box diagram. Now, here are some basic rules to write electronic configuration. Number 1, the Aufbau principle. It states that the principle states that electrons fill orbitals from the lowest energy orbital upwards. So the order of filling out of orbitals start with 1s, 2s, 2p, 3s, 3p, then 4s before 3d, 4p, 5s, 4d. So you need to write something like this: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5, and do a diagonal one arrow. So you have 1s here, then 2s, 2p, 3s, and follow the arrow. Look at my cursor. This is the order. Okay? So electrons will occupy the 4s orbital first before the 3d. So this is what is important in the syllabus, because we'll be learning about transition elements, the d block elements. So we need to understand how the electrons are filled out first. So we have to focus more on this, 4s than 3d. Now, the Pauli exclusion principle, where it states that each orbital can only hold a maximum of 2 electrons and they must be of opposite spin. This is important when you are drawing the electron in box diagram. So you are supposed to draw like this and not this and this. The reason is paired electrons can only be stable when they spin in opposite direction because the electrons are of similar charge. So in order to minimize their repulsion, they need to spin in opposite direction to counterbalance this electronic repulsion. Okay. Okay, next. Orbitals of subshell, according to Hans' rule. Orbitals of subshell refers to orbitals of the same energy. They must be occupied singly by electrons of parallel spin before pairing can occur. This will help to minimize inter-electronic repulsion. So it's important to fill up the electrons in single orbital first before pairing them up, because this helps to minimize electronic repulsions. How to write electronic configuration? So 1s1 is an example. 1 stands for principal quadrant number. S is the type of orbital, and 1 indicates the number of electrons in the orbital. So this is the electronic configuration and the electron inbox diagram for the first 20 elements for your preview. Just to take note, for the last two, potassium and calcium, we fill up the 4s and not the 3d, because 4s is of a lower energy level. Now, moving on to the transition metals known as the D block elements from atomic number 21 to 30. We use this noble gas to represent the first 18 electrons, so that we do not need to write so much. So we only focus on the 3d and 4s orbitals. So these are the electron inbox diagrams and the electronic configuration for the transition metals in this period. Okay, now there are some anonymous electronic configuration behavior, in particular chromium and copper. Starting with chromium. So if you look at the electronic configuration, it is written as 1s1, 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, and 4s1. By right, it should be 4s2 and 3d4. But why is it like this? Why the electron from 4s move to 3d? So the expected electronic configuration should be this: 4s2, then 3d. However, this is not stable. So to allow for more stability, the electron from 4s is actually in 3d. This is a more stable electronic configuration. Since 4s and 3d orbitals are about equal in energy by the time chromium is reached. So by having one electron in each orbitals, the inter-electron repulsion can be minimized. So having a half-filled subshell is actually more stable. This applies to copper as well. So why copper is not 4s2 3d9? Because a fully filled 3d subshell is more stable due to the symmetrical charge distribution around the metal. So remember, a half-filled subshell and a fully filled subshell is more stable. Okay, but for this one, the reason is more like, it's better to say that the electron should be in each 3d and 4s to minimize inter-electron repulsion. This will be a more reasonable reason. Okay? As for this one, for copper, it will be symmetrical charge distribution. Okay. So please know how to write both the electron inbox diagram and electronic configuration very well, following the 3 rules we have applied just now. The 3 principles here, in order to write the electronic configuration successfully. All right. Okay. So pair them out individually before, fill them out individually before pairing them. Just like when you take a bus, you will find an empty seat only when all the seats are occupied. you will then sit with someone else because there's no other available places. Okay? Now, so in summary, the order of filling out electrons is 4s before 3d. Remember this. But when you write the electronic configuration, when you fill out the electrons by indicating the position of electrons, right, you look at 4s and 3d. But when you write the electronic configuration, you have to still write the 3d first, then 4s. Now, bear that in mind. Okay? Each orbital can fill up to 2 electrons. Degenerate, which means same energy, orbitals of the subshell must be occupied singly and with parallel spin, opposite spins. Okay, and chromium and copper have anonymous electronic configuration, half-filled, fully filled. And the reasons are different. One is because to minimize electron repulsion. The other is for symmetrical charge distribution. Now, moving on to ground state and excited state, what is the difference? An atom in the ground state, where the electrons are in the orbitals of lowest available energy level. So atoms in the ground state are normally at room temperature. And most of the atoms will be in ground state at room temperature. The electronic configuration written so far for the earlier pages are all ground state electronic configuration. But there's a possibility that the atom could be excited, could be in the excited state when these electrons absorb energy and promoted to a higher energy level. These excited atoms become unstable and emit energy to return to the ground state. So we have the ground state, and when these particular electrons over here in the 2s orbital get excited, should I say absorb energy and move to the excited state, it will move to a higher energy level, 2p. So it is possible for such a scenario to happen. Okay? So you could have a case whereby the electrons from 2s move to 2p, or even from 2p move to 3s, or from 3s or 2p move to 3p. Okay. However, the electrons in 1s orbital do not get promoted because the energy gap between n equals to 1 and n equals to 2 is too wide. All right. Now, so when atoms gain or lose electrons, ions are formed. This is what we learned in O level. For anions, the general rule is that electrons are added to the next available orbital, the next energetically accessible orbital in the atom during the formation of an anion. So for sulfur, we have this electron inbox diagram as shown. All right. 3s2 and 3p4. So when sulfur gain 2 electrons to become sulfide, it becomes 3p6. Okay. So it looks like a noble gas configuration. That's what we have learned earlier on in the O-level syllabus. When ions are formed from atoms, they form noble gas configuration. As for cations, the electrons are removed from the orbitals with the highest energy. All right. So in example, we have aluminium. Aluminium, the highest orbital will be 3s and 3p. So electrons are removed from 3p first, and then the next one will be 3s. So we go by this order. All right. As for cations from the D block, example iron, remember this. Although 4s electrons are filled first before 3d, but when come to losing electrons, it will be the 4s that are lost first. This is because electrons occupy the 4s first. Okay, normally electrons will occupy the 4s first because the 4s orbital is of a lower energy level. But once electrons, right, are occupying the inner 3d orbitals, okay, so it provides some shielding from the outermost 4s electrons. So the 3d electrons is providing some shielding. So they actually repel the 4s electrons to a slightly energy level. Because of this shielding between the electrons, the repulsion causes the 4s electron to be promoted to a slightly higher energy level. Therefore, when ions are formed, it was the 4s electron that are lost first before the 3d. Please take note of that. Because of this reason, because of the shielding and repulsion causing the 4s electrons to be moving upwards to a higher energy level. All right. So in the formation of cations, the 4s electrons are lost before the 3d electrons. So these 4s electrons lost to form the ion 2+. Next, what is isoelectric species? They are species with the same total number of electrons. That's it. All right. So ions and atoms of different elements may turn out to have the same number of electrons. Now, this is another word example for you to work on. You can pause this video before attending the question, and then on the video, resume the video to check your answers. Now, in this question, you are supposed to write the electronic configuration for each species and draw energy level diagram to illustrate each electronic configuration. So starting with sulfide. So when sulfur gained 2 electrons, the electrons are taken into the next available orbital. Okay, so it will be the 3p, correct? Because there is still available spaces for the 2 electrons to be added to 3p orbital. And this is the energy level, 1s, 2s, 2p. Take note that 2p and 3p orbitals are degenerate. They have the same energy level. Okay, so draw like that. As for calcium, 4s2, it lost 2 electrons from the 4s orbital, so 3p6. Copper plus, not 2 plus, it lost only 1 electron and it has to be from the 4s, not 3d. Okay, so it will form this. You have the 3d orbitals. Now, moving on to the relationship between electronic configurations and the periodic table. Based on the electronic configuration of elements in periodic table are grouped into 4 blocks, S, P, D, and F blocks. The name of each block is determined by whether an S, P, D, or F subshell is being filled in successive elements of the block. So the S block is mainly the group 1 and 2. The D block is the transition metals from group 3 to group 12. 13 to 18 are the P block. Okay, so this is the subshell they have, and F blocks here. So 1s, 2s, 3s, 4s, 5s, 6s, 7s, 3d, 4d, 5d, 6d, 2p, 3p, 4p, 5p, 6p, 4f, 5f. So this is the subshell they will fill up. Now, the horizontal rows is called period. We have learned this before. They have elements in the same period will have the same number of electronic shells. The period number of an element is the number of electronic shells occupied with electrons in an atom of that element. The vertical column is called groups. So elements with the same number of valence electrons and hence similar outer electron configuration will be positioned in the same group, or will be arranged in the same group rather. For group 1, we call them alkaline metals. Group 2, alkaline earth metals. 15, 16 are less familiar terms, just for information. 17 is halogens, 18 is noble gases. Okay? Now, because chlorine is a group 17 element, its electronic configuration of valence shell will be Ns2, Np5, and refers to the principal quadrant number. And because chlorine is a period 3 element, N equals to 3. All right. So N is related to the period the element in. So this is the electronic configuration of chlorine. Okay. Now, moving on to electrostatic effect. So what is it? Electrostatic effect is the attraction of opposite charges and repulsion of like charges, which plays a major role to determine the energy state of atoms and hence influence atomic properties like atomic size and ionization energy, which we will elaborate later on what is ionization energy. The main factors that affect the strength of electrostatic attraction between the nucleus and the electrons are, number one, number of electronic shells. So if the number of shells increases, the principal quadrant number N of the outermost shell will increase. The distance between the nucleus and the valence electron will increase. And therefore, electrostatic attraction between the nucleus and the valence electron decreases. Nuclear charge Z. If the number of protons increases, nuclear charge increases, which causes the electrostatic attraction between the nucleus and the valence electron to increase. Now, another factor is shielding effect, or we call it screening effect by the inner electrons. So inner electrons are shielding the valence electron from the nucleus. So shielding effect experienced by the valence electron will increase if the number of inner shell electrons increases. This will cause the electrostatic attraction between the nucleus and the valence electron to decrease. And these two factors combine to affect the effective nuclear charge. The effective nuclear charge is the resultant positive charge experienced by the valence electron in a multi-electron atom, taking into consideration the shielding effect of the inner electrons, where effective nuclear charge equals to Z minus S. Z is the proton number, S is the shielding effect. So this is the effective nuclear charge. It's the overall effect of the nuclear charge and the shielding effect. Okay, so if the effective nuclear charge increases, the electrostatic attraction between the nucleus and the valence electron will increase. It makes sense, right? When discussing the trend of atomic properties across a period, it is common to consider factor 2 and 3 together and state their combined net effect. So we normally use effective nuclear charge when we describe or explain the trend of atomic properties across the period. And in the subsequent chapters, we will be making use of these factors that I'm explaining to explain the trends in variations in, number one, atomic radius and ionic radius. First, ionization energy, known as IE, across a period. First IE down a group, successive IE of element, and electronegativity. So what is meant by shielding? Let me explain in detail. Since all electrons are negatively charged, they will repel each other. So the electrons in the inner shell will repel the electrons in the outer shell and prevent them from experiencing the full effect of the actual nuclear charge. This is called shielding. So we have the valence electrons over here, but the inner shell electrons is shielding them from the attraction by the nucleus. So the greater the shielding of outer electrons by the inner shell electrons, the weaker the attractive force between the nucleus and the outer electrons. And electrons in the same shell actually provide very poor shielding effect for one another, okay, because they're in the same shell. So for a given shell, the shielding ability of electrons decreases in this order. So S having the highest ability, followed by P, D, and F. D and F electrons usually provide very poor shielding effect for outermost electron. Because the D and F orbitals, they are rather diffuse, meaning the electrons in these orbitals are spread over a large area, not concentrated. So when they are not concentrated, they cannot provide good shielding effect. Now, let's move on to the next part on atomic radius. What is atomic radius? It is the half, the shortest nuclear distance found in the structure of the element. So the observed radius of the atom depends on how atoms bonds or interacts with its neighbor. So when we talk about metal, the metallic radius of an atom is actually half the internuclear distance between two neighboring atoms in a metal. So the metallic radius is actually restricted to elements that form metallic lattice. You have to be very strict about that. Metallic radius is for metals, structures of metal lattice. All right. So we take two atoms that are close to each other, and it will be half the distance between the atoms. Okay. Between the nucleus of the atoms, actually. All right. As for covalent substances, right? Covalent radius of an atom is half the internuclear distance between two covalently bond atoms. It's very similar to metallic radius. As for van der Waals radius, it refers to half the nuclear distance between atoms which are not chemically bonded. So, van der Waals radius is most easily determined for nonmetals and is very useful for lighter noble gases which do not form chemical bonds. All right. Like noble gases. Now, this is the variation in atomic radii of the elements across the different periods. Okay, so go down, up again, and down, up, down. Okay, so let's examine the trend in atomic radii across the period from period 3 elements, sodium in group 1 all the way to argon in group 18. So you can see that the atomic radius in general decreases, correct? As read from the data. So what is the explanation for the atomic radius? Across the period, the number of shells remain the same. It's the same number of shells because they are in the same period. N equals to 3, right? However, across the period, the number of protons increases and nuclear charges increases. Nuclear charges is the charge of the nucleus. So with increase in number of protons, the nuclear charge will increase. The number of electrons also increases. However, these electrons are added to the same outermost shell, and therefore shielding effect remains almost constant. Because the electrons are added to the same outermost shell, so the effect of the shielding effect by inner electrons will be about the same. So if we consider shielding effect and nuclear charge, the effective nuclear charge increases. When effective nuclear charge increases, the electrostatic attraction between the nucleus and the valence electron increases, which causes a decrease in the size of electron cloud. Okay? Which means the electrons are closer to each other, which means the size of electron cloud decreases. So atomic radii decreases across the period. So make sure you have all these points here when you're asked to explain the trend of atomic radii. Now, how about trend in atomic radii down a group? Okay, down a group, if you take a look at group 17 elements, the atomic radii actually increases. Why? Because the number of electronic shell increases. The distance between the nucleus and valence electron increases. So yes, there is increasing nuclear charge. However, electrostatic attraction between the nucleus and valence electron still decrease. This results in the increase in size of electron cloud. So the effect of number of electronic shell increases overtake the nuclear charge. So there are two factors affecting it. One is number of electronic shell, one is nuclear charge. So it's apparent that this effect is greater than the other. So it supersedes that. As a result, the atomic radii increases down a group. As for ionic radius, what is ionic radius? It's defined as the radius of the spherical ion in the ionic compound. So if you examine period 3 again, so these are the ions of period 3 and take a look at their radius. For atomic radius, there's a general trend of decrease. But for radius, it decreases. And then when it comes to the negative ions, phosphide is so much larger than the rest. Then it decreases again. Okay, so what is the reason for that? So for the cat ionic radius, okay, the positive ions, in general, the radius of the ion is smaller than the atom. That is for sure. Okay, based on the data, all of it is smaller. The reason is because both cation and the parent atom have the same number of protons, which means they have the same nuclear charge. However, because the atom loses electron to become cation, so the cation will have one less electronic shell. With that, the electrostatic attraction between the nucleus and the valence electron will increase. Okay? Because the valence electron now become closer to the nucleus. Okay? This results in a decrease in size of electron cloud. Okay, so the distance between the nucleus and valence electron is very critical. It will really affect the radius to a very large extent. Let's talk about the anions. The anionic radius is the opposite. The anion is of a greater radius than the parent atom. Why? Both the anion and the parent atom have the same number of protons, hence they have the same nuclear charge. However, anion has more electrons. So with more electrons, there is more repulsion between the electrons. With that, the electrostatic attraction between the nucleus and the valence electron will decrease because of the repulsion. So it results in an increase in the size of the electron cloud. Now, for isoelectric species, which means the same number of electrons, what is the trend? So across the period, we observe that the ionic radii of isoelectric ions actually decrease. So this refers to the same number of electrons, and this refers to the same. Okay, we are comparing them separately. So between the cations, we notice that the radius decreases. Even so for the anions as well. What is the explanation? Now, sodium, magnesium, aluminum are isoelectric species. Hence, their valence electron experience the same shielding effect because they're the same number of inner shell electrons. However, from sodium to aluminum ion, the nuclear charge increases. Aluminum ion has more protons than sodium. So effective nuclear charge increases because of increases in nuclear charge. Therefore, electrostatic attraction between the nucleus and the valence electrons will increase. This results in a decrease in the size of the electron cloud. Similar explanation for the anions as well. But there is a sharp increase in ionic radius from aluminum to phosphide. Why is it so? Because phosphide, if you write down the electronic configuration of the ions, it has one more electronic shell. So with one more electronic shell, despite phosphide having a larger nuclear charge, the valence electron are actually less strongly attracted because you have one more electronic shell. So it is further away from the nucleus. Consequently, the ionic radius is larger despite the nuclear charge. Now, let's move on to the next objective on ionization energy. I'm going to call it IE here for convenience. So what is first IE? First IE of an element is the energy required to remove 1 mole of electrons from 1 mole of gaseous M atoms to form 1 mole of gaseous M plus ions. So the state of the species involved are in gaseous state, and we are referring to them as 1 mole, 1 mole, 1 mole. And we are referring to atom, not molecule. Okay, so please remember the definition well and how you write the half equation. All right, As for the second IE, is the energy to remove 1 mole of electron from 1 mole of gaseous M plus ion to form 1 mole of gaseous M2 plus ion. Okay. And ionization is an endothermic process, which means energy absorbing. And IE are positive values since energy needs to be absorbed to overcome the attraction between the electrons and the nucleus. And IE affect the type of bonds formed by the atom with other atoms. So if we have elements with low IE, it will be easy to lose an electron to form cation, resulting in ionic bonds being formed. So you may like to pause the video to do the first question here. Write an equation to represent the reaction in which enthalpy change is equal to the third IE of sodium. This is the answer. And you can pause the video for the next question. Name the enthalpy change for the following reaction. It is not just third IE, but it's first, second, and third IE together. Now, let's look at the trend in IE across a period. So this graph shows the first IE against atomic number or the first 30 elements from period 1 all the way to period 4 elements. So you can see there is a general increase across the period. But when we talk about the transition metal, the increase is not so much. And there are some exceptional cases, okay, which we can talk about it. Now, there are 3 key points to take note when we discuss the trend of first IE across the period. Number 1, the general, I repeat, general increment across the period, and some irregularities, like between group 2 and group 13, group 15 and 16. Yeah, here. Group 2 elements, I think, and some group 13 and group 15 and 16. Okay, let's look at it individually. So starting with the general increment. So in general, the first IE increases across the period. Why? Number of shells is the same. Number of protons increase, nuclear charge increases. Number of electrons increases, but electrons added to the same outermost shell. So shielding effect, almost constant. It's like copy and paste from the previous explanation of atomic radius. So effective nuclear charge increases. So electrostatic attraction between nucleus and valence electron increases, which result in increase in energy required to remove valence electron. So you need to have all these points there as detailed as possible in order to score the full mark. So first IE in general increases across a period. Starting with group 2 and 13. Okay, how do we explain that? So the first IE of boron, if you examine closely, okay, where's boron? It's lower than beryllium. Okay. So you have this very strange. And also aluminium and magnesium here. So we look at this and this. Okay. Why? Okay. For magnesium and aluminium, right? Okay, you can use the same explanation for boron and beryllium also. For aluminium, the 3p electrons to be removed from aluminium is of a higher energy level than the 3s electron to be removed from magnesium. So less energy is required to remove the 3p electrons in aluminium than the 3s electron in magnesium. Okay, so I repeat, the 3p electron is of a higher energy level. So why IE of aluminium is lower? Because it takes less energy to remove the 3p electron of a higher energy level, easier to remove. So the IE of aluminium happen to be lower. How about 15 and 16? O and N and S and P. So O is 8 here and here. Okay. The next two discrepancy. So if you talk about phosphorus and sulfur, you can use the same explanation for oxygen and nitrogen. The explanation is different from the first one. The 3p electrons to be removed from S, right? Can you look at this? This is a paired electron. While that to be removed from P is a unpaired electron. So between the paired electrons in sulfur, right, there is inter-electronic repulsion. So because there's already repulsion between electrons, it's actually easier to remove, but you should say less energy and not say easier. Easier is just a layman term to help you understand, but it's actually more precise to say less energy to remove the paired 3p electron. And therefore, the first IE of S is lower. Now, how about the second IE? Okay, so I will leave it to you to do yourself. Okay, in general, second IE should be higher than first IE of each element because definitely more energy to remove electron from positive ion. And of course, the exceptional case will be different because the electronic configuration of the ions will be different. So you may be asked to compare the second IE between elements. So just take note of that. I shall not go into that. Maybe when you attend questions, then we will see. Now, what is the trend in first IE down a group? So for group 1, the first IE in general decreases. Same for group 17. So in general, down a group, right? The reason is because the number of electronic shell increases. So the distance between nucleus and valence electron will increase. And despite the increasing nuclear charge, despite that, because as I said, this is a very significant factor, even more significant than nuclear charge. The electrostatic attraction between nucleus and the valence electron will decrease, which result in a decrease in energy to remove the valence electron from the atom. So the first IE in general decrease down a group. And you can pause the video to do this. Predict and explain which one has a higher second IE. Aluminum, silicon, and oxygen, fluorine. Can pause the video, attempt the question before checking the answer. Now, for the first example, aluminum and silicon, okay, the strategy to do this kind of question is to write down the electronic configuration so they can see clearly how the electrons will affect the IE. You must do this. Okay, it is an important strategy. So, second IE involves the 1+ ion, correct? So it's aluminum ion and silicon ion, 1+. Now, this is the electronic configuration of aluminum ion and silicon ion. So the 3p electron to be removed from Si+, right? You can see that 3p is of a higher energy level than 3s. So although silicon is to the right of aluminum in the period, but silicon plus has a lower second IE because the electron to remove is from the 3p electron, which require less energy to remove. As for oxygen and fluorine, the reason is a bit different. It's not about higher energy level. It's about paired electrons. So for O+ ion, okay, if you sketch the electron inbox diagram, it look like this. For F+, right, it will look like this. So you will see there is inter-electronic repulsion between the paired electrons in the 2p orbital of F+. So less energy is required to remove the 2p electrons. So actually, there is a certain standard answer. For cation or metal, it has to do with energy level, or sometimes with electronic inter-electronic repulsion. For anion, it could be also due to electronic repulsion or energy level. So if you look at the previous answer, it is very similar. Very similar. Okay? Can? Okay. Now, so what is the trend in successive IE of elements? So we're talking about the same element having successive IE. So how do you explain the trend? So the trend is, of course, it increased because once the first electron is removed from the neutral atom, each successive electron is removed from ion of an increasing positive charge. So the remaining electrons are attracted more and more strongly as you remove the electrons from the species. Another explanation is you can say that, as the electrons are removed successively, the number of protons remain the same. So nuclear charge remain the same, but number of electrons decreases. So the electrostatic attraction between nucleus and the remaining electrons will increase, which result in more energy required to remove every subsequent electron. How do you deduce group number from successive IE data? So you can see that for potassium, right, from first to second, there's a large increase in IE. So this shows that potassium belongs to group 1 and has 1 valence electron. So if you see a significant jump in IE, okay, then it will correspond to the group and the valence electron number it has. So the explanation will be more energy is required to remove the second electron from potassium because the second electron is located in a different shell, which is an inner shell closer to the nucleus or nearer to the nucleus, and hence experience a stronger electrostatic attraction, which explains the large jump between the two IE. Okay? So if there's a large jump between first and second, it will be group 1. Second and third, group 2, something like that. Give you a word example. Can you try this question? Pause the video. Okay. In this question, you are given the first AIE of an unknown element. So what you need to do first is to deduce the group of this element, right? You need to determine the difference between the IE. So what the strategy is to take the first and second to find the difference and do that for the subsequent IE. And you notice that there is a large jump here. Here, can you see that? So first, second, third, fourth, fifth to sixth. So group 15, correct? Yeah. So how do you explain this? There's a large jump between the fifth and sixth IE. So more energy is required to remove the sixth electron because it's located in the inner shell. So there are 5 electrons in the valence shell. So this element is in group 15. How about this question? Try this question and pause the video. Now, this is a different format of question. So instead of giving you the data, they present it in graphical form, in bar chart form. So where do you see the significant jump? You can see it's here, right? Group 1 to 2, am I right? Is first and second. Yes, I hope you're able to see that. So there's a large jump between first and second IE. So the explanation is a repeat. Standard answer, standard question. More energy required to remove the second electron as is in the inner shell. So there's 1 electron in the valence shell. It has to be a group 1 element. Now, to deduce electronic configuration and other information from successive IE. So take note that when you look at a question like this, right, you sometimes will see the question present in logarithm form because they want to allow for larger range of IE because the value could be very large. So when you log it, right, it will be a smaller scale. It will be able to fit more conveniently on the vertical scale and also to make any large differences more apparent. So it's easier for the observer. There's a reason why they do that, okay? Now, from here, you can see that for this element, right, there are 6 electrons from the 2p orbitals and in the 2p subshell and 2 electrons in the 2s orbital and 2s subshell. So you can tell that this is the 4th, 3rd, 2, and 1. So you can actually tell what is this element already. No. So some information that we obtain from this is you can count that there's how many? There's a total of 19 electrons. And from 19 electrons, you can write down the configuration. Okay. There are 4 electronic shell. There's a large jump in IE, when the electron is removed from a different shell, the one that is inner and the nearer nucleus, and hence experience a stronger electrostatic attraction. The graph also shows 3 such large increase, 1, 2, and 3. So with 3 large increase, it means you have 4 shells. All right. There's 1 valence electrons here because there's a large increase after that. So it must be a group 1 element. So I will not go through the reason anymore. Okay. Now, so data of successive IE of element provide evidence for the existence of electronic shell of different principal quadrant number and subshells. Large jump observed in 2 successive IE, which means the electrons are removed from different shell. When there's a moderate difference, meaning a small jump but not a very large jump between 2 successive IE, it could be removal of electron from different subshell like this. 3p, 3s. 2p, 2s. It's a small jump. So the small jump between the 7 and 8 IE is due to removal of electrons from different subshell. The energy gap between subshell is not as big as that of between shell. It's sometimes not discernible, meaning not observable. However, a small jump is expected between the 15 and 16. But you see, is obviously these two are from different subshell, but it's not observed in the graph. But that doesn't mean it's not of the different subshell. Okay, moving on to the last concept of the day, electronegativity. Then we are done. Electronegativity of the molecule is the relative measure of the ability to attract bonding electrons. So if you look at this graph here, we can see in general, across a period, there's an increase in electronegativity. The reason is because as the number of shells remain the same, the number of protons increase, nuclear charges increase, the number of electrons also increase. But these electrons are added to the same outermost shell, so shielding effect is almost constant. Effective nuclear charge increase. So electrostatic attraction between nucleus and the bonding electrons will increase because of increase in effective nuclear charge. So when electrostatic attraction increase, electronegativity will increase. But across a period, across down a group, you see that electronegativity, right, decreases. Yes, it decreases. Lithium, sodium, potassium. Why? Because when number of shells increase, the distance between the bonding electron, not valence, bonding, because electronegativity is defined based on bonding electrons. So we have to be careful in the terms we use here. Distance between nucleus and bonding electrons increases. Despite the increasing nuclear charge, this factor is not significant here. The number of shells and the distance is more important. The electrostatic force of attraction between nucleus and bonding electrons decreases, so electronegativity decreases. Now, last page. When 2 atoms of similar electronegativity are covalently bonded, you form a non-polar bond. We shall elaborate more on chemical bonding in the next chapter. So if the difference between the electronegativity of 2 bonding atoms increases, the covalent bond will become more polar. At the same time, the ionic character of the bond also increases. So with sufficient difference, it will be ionic bond. So in general, if the difference in electronegativity between the 2 bonding atoms are less than 0.5, we classify as non-polar. Between 0.5 to 1.6 is polar covalent. More than 2, confirm ionic. So in general, metals have low electronegativity, tend to lose electrons. Non-metals have higher electronegativity, it gains electrons. So electronegativity is an important concept that can relate to metal, metalloid, non-metal properties of elements. All right, so that's it for today. I hope you learn a lot. So if you like my channel, I will hope that you can subscribe to it, and with greater viewership, I will post more videos for the subsequent lectures and lessons. Thank you.